Welcome back. This is our third video in the kinetics unit. If you have not yet done the lab on rates of reaction with the sugar, please do that before you go any further in this video. It's kind of fun to have an idea of what the answers are in this list before we go through the list, and you doing that lab is going to allow you to explore that activity. So again, please pause and come back when you've done the lab and the analysis. Don't forget to do the analysis before you come back. All right, so now if we're moving on, I'm assuming that you've done the activity, so you have a chance to kind of figure out what ideas are going in here. Okay, so we're taking a look at rates, a little bit more closely at rates. So we can alter the rate of the reaction two different ways. We can change the number of collisions, which is what you did when you did the activity with the sugar. The other thing we can do is change the percentage of the collisions that are effective. So how do we get more effective collisions? Well, we throw in a catalyst. We lower the activation energy by offering an alternative pathway for the catalyst. So you were not able to do, You were not able to do this with the sugar cube because there is no catalyst for the dissolving of sugar. But we can take a look at what you did do, and that is, how can you change the number of collisions? You were trying to change the rate of the reaction. We changed the number of collisions. So think about all the different things that you did. This seems really simple, but stirring or mixing will get those molecules to collide more often, right? You get them moving, so they're going to collide more often with the water molecules. They're going to interact more with the water molecules, so they're likely to dissolve. If you increased the temperature of the water, you were able to get more solid to dissolve because solubility typically increases as temperature increases. Again, by increasing the temperature, what are you doing? You're making the molecules move more. You're giving them more kinetic energy. More kinetic energy means more collisions, which means a faster reaction rate. Now, this next idea comes from one of the analysis questions. What if you had used a sugar cube instead of a teaspoon of sugar? What would you have to do to get that sugar cube to dissolve? Putting that sugar cube sitting as a solid would be difficult. If you said breaking that sugar cube up, that's really increasing the surface tension. So if you have a solid, surface area. If you have a solid, you want to crush it, which will increase the surface area. More surface area means more particles exposed to the other things that it's reacting with, so the reaction is going to happen faster. So notice I'm kind of referring back to the ideas that we started to see in the gas unit. What are we doing with the particles to allow, in this case, more collisions to happen? So if we expose more of the particles simultaneously by increasing the surface area, we will get more collisions. Next idea comes from another question, the HCl magnesium lab. What if we had changed the concentration? Your rate would have gone down if you had used 0.1 molar because there's not as much HCl there, right? Moles per liter, if you take the moles away, there's going to be fewer molecules there to collide with. So a greater concentration gives you more particles, more collisions. A smaller concentration gives you fewer particles, fewer collisions. Now, one thing we couldn't do was take a look at the reaction in terms of gases because we just didn't have any involved. But if you can alter the volume or the pressure of a gas, this is strictly for gases. By the way, this was strictly for solids. If you can alter the volume and therefore alter the pressure, if you decrease the number of collisions, less reactions. If you increase the number of collisions, more reactions. The last idea here, you just can't know. I just got to give it to you. And it's simply the nature of the actual reactants themselves. So what you're working with is going to control the rate. So you may, if you have to do one particular reaction, you may not get the rate to go any faster than it already is, simply because of what you're working with. So that's something else that influences the rate of reactions. All right, so that is rates. What I want to do is move on to mechanisms. We're not going to do a whole lot of work on mechanisms, but I just want to introduce it to you since I can. So the mechanism is really a step-by-step picture of how the process takes place. So first substance A collides with substance B and they create this. And then substance AB collides with, so on and so forth. So the mechanism is really a step-by-step process that shows you how the reaction is taking place. It gives you a couple pieces of information. So first thing is, when we draw a mechanism, all our mechanisms are going to be two-particle collisions. Because having two things collide is hard enough. To try and get three things to collide with the right orientation and the right amount of energy is near impossible. So our assumption is that any step in the mechanism is going to be a two-particle collision. It could just be a bond breaking, but if it's going to be a collision, it's going to be only a two-particle collision and not a three-particle collision. All right, so once you look at that mechanism, and I'll show you one or two in a moment, once you look at that mechanism, you can learn a few things about it. We call the slowest step in the mechanism the rate determining step. Determining step. The rate determining step is what's going to control how fast your reaction happens. So example, think about if you're driving into the city and everybody's moving along really, really nicely, and then all of a sudden you slow down. And why do you slow down? Because there's a guy going much slower than everybody else in the road. So he is the rate determining step. You can't go any faster than what he's going because he's limiting your access to the road. So the rate determining step is always the slowest step in the mechanism. You can't go any faster than the rate that the slowest step proceeds. So it doesn't matter if you want to go 90 miles an hour. If the person in front of you is only going 60 miles an hour, you're not going faster than 60 miles an hour. The other things you can get from the rate determining step are the intermediates. Now, an intermediate is not the same as an activated complex. An intermediate is actually a relatively stable molecule that you get as a product at the end of one of the steps in the mechanism. So an intermediate is really a temporary product. So it appears from one of the steps, but then in a subsequent step somewhere it gets used up. So the intermediate appears temporarily, but then it disappears. The other thing a mechanism can show you is a catalyst. A catalyst is kind of the opposite of an intermediate. A catalyst goes into the reaction. So the first time you see it, it's on the reactant side. It goes in as a reactant, but then further on down the mechanism somewhere, it comes out as a product. So an intermediate, in the end, when you draw your final overall reaction, the intermediate isn't there because it was formed, but then it disappears. The catalyst is technically there on both sides because it goes in, but then it comes back out. So an intermediate is like it was never present. A catalyst is like it never left. And in addition, you can get the reactants and the products. So like I said, we're not going to spend a lot of time on mechanisms, but I just wanted to give you two examples. Okay, so first one is how palladium actually acts as an organic catalyst in a bunch of reactions. So here I've got the slow, fast, fast step. So 3 steps to the mechanism. Each one is a 2-particle collision. And so we've got the slow step is the first step. So the slow step is the rate determining step. This is the step that's going to control how fast the reaction happens. Once we get these PDHs formed, then we can go on and do the rest of the reaction. Okay, so let's take a look and see if we can figure out what the intermediates are. Intermediates are substances that get formed but then get used up further down in the reaction. So if you look at the equation, in the first step we create PDH2. But in the next step, we actually have one of the PDH2s get used up. So there's an example of an intermediate. Okay? Notice that the second PDH2 gets used up in the third step. So the PDH, not H2, I'm sorry, the PDH is an intermediate in this reaction because it gets produced, but then it gets used up later on. Another intermediate is the product of the second step. C2H5PD gets produced, but then notice that it gets used up in the third step. So there is an example of another intermediate. Okay, if we look at other stuff, hydrogen is only on the products or on the reactant side. C2H4 is only on the reactant side. C2H6 is only on the product side. So those three are reactants and products. But palladium, 2 palladiums go in, but in the end, 2 palladiums come out. So what is this really an example of? This is an example of a catalyst. We can cross catalysts out, but because they started as a reactant and ended as a product, they are really a catalyst. So we can do a couple things here. We can say that our overall reaction is everything that's left, so the H2 plus the C2H4 producing C2H6. There's our equation. But then palladium is going to be our catalyst, and PDH and C2H5PD are actually our intermediates. So did you see how that works? All right, your turn to try. This is the last thing we're going to do. Here's another mechanism. So take a moment, pause the video, take a moment and see if you can figure out what the overall reaction is. So identify the reactants and products, identify any intermediates, and any catalysts. And what's the rate determining step? Okay, so hopefully you paused. We're going to go through and cross things out like we did before. So I see Cl plus and Cl plus. I see Al4 minus and Al4 minus. I see H plus and H plus. And I see AlCl3 and AlCl3. Those are all the things that I can cross out. So what I'm left with is my reaction. So 2 chlorines plus C6H6 give you C6H5Cl plus HCl. The rate determining step is the second step because it's the slowest step that happens. And now, what about these things that I crossed out? AlCl3 appears first on the reactant side, goes into the equation, but then gets kicked out in the end. So that is an example of a catalyst. AlCl4 minus gets generated in the first step, but used up in the third step. So that's definitely an intermediate. Cl plus gets produced and then quickly used. That's another example of an intermediate. And then finally H plus gets produced and then used very quickly. So that's your third intermediate. So we've got 3 intermediates, 1 catalyst, 2 reactants, and 2 products. All right, and that concludes Unit 9. That concludes what we're doing with kinetics. So you've got some problem sets to work through a little bit, but we will very quickly move on to equilibrium, which is Unit 10.